Okay, anybody have any specific problems that we need to deal with? Um, whether it's based in the review document or not, doesn't matter. I want to be sure and get your concerns covered first before we go on with my structured plan. No, if she think of something, you got one?
It's more like any question that has to deal with the grams of a substance to take it into a percentage, like any that has to do with those different, like with, I think it might be abundance problems, but
Okay. Do you have an example?
I was just looking.
Okay.
I haven't seen.
You got one?
But there was some
homework. That this was like in the same page. I don't understand that they give you a formula.
Okay.
You have to find like the atom, but how come this formula you have to do times? Sorry. I can make that bigger.
Atom of nitrogen in one molecule. The number of atoms of nitrogen. Oh, okay. Now, what was your question?
Well, like, I got the bottom two answers wrong because they said that there's 2 atoms of nitrogen in the nitrogen. How are you gonna know?
Well, they're not two in ammonia. It must have been a different molecule.
Like on this part right here, why do they have 2 times?
Oh, yeah, because there are two nitrogens in the hydrogen. And N2H4 is hydrogen.
So can you just have to know it, or like, I'm so confused.
Yeah, the clues are right there. Give me the problem and what does it say? Is it in a word problem?
It is, but I didn't take the picture of the.
Oh, okay. Well, let me see if I can deduce it from the answer.
So it was asking you for the atom. They give you like
The number of atoms in 4.56 grams of hydrogen. Okay. So if you're given 4.56 grams of hydrazine, which is that formula, it wants you to convert to the number of atoms of nitrogen in that sample, correct? That's what I get.
atoms, yes.
Yep, number of atoms. Okay. You need to bridge, the gap that you need to bridge is between mass and numbers. Okay, so you need numbers of atoms. And the only bridge we have between mass and numbers is Avogadro's number. That's the conversion factor that takes you from mass to numbers. This is in grams, so that's good. Right? We can convert that into moles of hydrazine, that whole unit right there. Okay, so we've got oh no, I'm sorry, should have stopped me. What we need is to, it's not Avogadro's number. That's the bridge. It's molar mass. Okay, did I confuse anybody? Okay, molar mass is the bridge between mass and numbers. So you need molar mass of this compound, which would be 2 times 14.01 for 2 nitrogens, okay? And 4 times 1.01, and this is grams per mole, for the hydrogens. Okay. Remember how to do that. That's the molar mass of hydrazine. Okay, 14.01. And these numbers, you get them off the periodic table here, rounded off 2 places. I didn't have to look because I've done it so much. I just have them memorized. Okay, so that's 28.02 for this one and 4.04 for that one. And so we have a molar mass for that molecule, that compound, of 32.06 grams per mole. 32.06 grams 1 mole. And that'll bridge the gap into numbers. Then we have Avogadro's number. Make some more room here. I think I'm gonna need it. So we cancel grams, right? Denominator, numerator. We got moles. Now we want to get rid of moles, numerator, denominator, and convert it to numbers. And this is numbers of molecules of hydrazine. That's as far as you've gone at this point. But they want to know how many atoms that is. If you got that many molecules, but there are 2 atoms of nitrogen for every molecule of hydrazine, that's molecules.
That's where I'm confused, like, where is that number 2 comes from?
Right here.
But we already calculated the molar mass, right?
Right. That only got you how many molecules of hydrazine there are. Okay. The only way we could do it the way you're thinking, to go directly to atoms of nitrogen, is if you figure out how many of those grams is due to nitrogen. And that's one way to do it.
So one can you tell, you have to use 2 in
When-
one.
Okay. When you calculate the number of moles of the compound, you haven't drilled down into the number of atoms yet. You're only talking about the number of moles of the compound. This tells us the number of moles of compound. And this takes us to the number of moles of atoms. You could do that first. Like once you get moles of compound, you could say moles of atoms. Right? It works either way. Because this is a chain conversion, multiply, 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 multiply. The order doesn't matter.
Is that because there's 2 sets of that compound? That you have to use it to?
There's only one compound, but there are 2 nitrogens for every compound. For every molecule of compound, there are 2 atoms of nitrogen.
And how come, we don't use the word on hydrogen?
Because that's not the question. Question is nitrogen. We could do this. We could do this for hydrogen, right? We could say 4 atoms of this is nitrogen, but we could say 4 atoms of hydrogen for every molecule. If the question were how many atoms of hydrogen? Yeah. So up to this point, right here, we're still talking about molecules, right? You could go to nitrogen, you could go to hydrogen, either way. The conversion factor is 2 to 1. There's a 1 up here. Right? For every one of these, there are 2 of those. 2 to 1, 4 to 1. 2 to 1, 4 to 1. And it takes some practice. And then you just run the numbers. This is the thinking part. All you do now is crunch the numbers. Right? This times that, times that, times that, divided by this, divided by that, divided by that. And you chain them together.
Something up with this was like they call it a movement where you can take like when do you use Avogadro's number between molecules and moles to atoms and
See if that helps.
yeah, so it'll like depending on what direction you go in, like if you're starting at grams like we did, it'll tell you, okay, this is what you need to have 1 mole for every gram and have those 1.5. So it's kind of fun thing was I was really confused. And well, I got it to the atom, but like how did they know that was 2 atoms? But I guess you just go with
The formula.
okay.
Yeah. Right? It's 2 to 1 or 4 to 1.
But you should see if this is accurate, like if I'm using misinformation.
Okay. Let's see. They say formula units, which is for universally accepted.
They don't generally try to get, yeah, okay. Cause I was.
This is the molar mass of that compound, but it could be a molecular compound, it could be an ionic compound. If it's an ionic compound, then formula unit is proper. What if we use something like this, glucose? If we found out how many molecules of that were in, say, a mass of, I don't know, 200 grams. We found out it had so many moles of the compound. Once we found out how many moles of the compound, then we could convert that, say we wanted to know how many moles of carbon you have. So for every mole of compound, you have 6 moles of carbon. Yeah, the formula tells you everything you need to know. And this is dimensional analysis. I mean, it's just conversion factor, pure and simple. All right. Did you figure out which one you wanted to do?
I think it was something similar to this, but they took the amount of like the percentage after they got the amount of not average.
Percent by mass, is that what you're looking at?
I think so.
Okay. If we could find one, maybe we'll come across one. Right. Anybody else? On camera, off camera? Okay. So let's look at some, and then if interrupt me if you figure out which one it is, or if I don't have one highlighted, you see one fly by that you want to stop on, just holler and we'll do that. Okay. So we're going to start with chapter 3. And the reason I'm designating chapter 3 is because apparently for this review document, I start renumbering with chapter 4. Okay. So we're going to do the first one first. Naturally occurring copper exists in 2 isotopic forms. See copper 63 and copper 65. Okay. That's given. The atomic mass of copper is 63.55 AMUs. This, what they're telling you there is this is 63.55 atomic mass units, average atomic weight, atomic mass. So it's a weighted average of those isotopes. That's what that value means. What's the approximate natural abundance of copper 63? So we're looking for the percent abundance of this one. And we have to use some algebra to do this one. Let the we're going to have to work from, I think we're going to have to work from assuming, yeah, we're going to have to assume that the mass of this isotope is 63 and the mass of this one 65, because it wasn't given to us. We know that the only one that has that value assigned to it is carbon 12. Remember that? Okay. So these would actually have something different, a little bit different than those values, but we're not given that, so we have to work from these values. All right. So how would we calculate this value from that value? Well, what we would need is the abundance of this copper isotope and the abundance of that copper isotope. So we would have the abundance of this one. If we say the abundance is equal to X, right, then the abundance of this one is equal to 1 minus X. And what I'm saying there is, if we were still in percent, this would be 100 minus X. But I'm making I didn't tell you, I was changing this to decimal abundance. This is decimal abundance. The math works better. So this would be something less than 1. And this, of course, would be less than 1 because we're subtracting it. All right, if we have those values, then in order to calculate this value, what we have is that decimal abundance times the mass of that isotope. Right, that equals a value. And then we add to it the abundance of this one times its relative mass. That. So we add those two together, that gives us 63.55. If we put values in here like 0.45, 45%, and this one would be 0.55, 55%, wouldn't it? Did I lose you already? That's algebra, right? If you're in algebra now, then it might seem strange. If you have algebra years ago, it still seems strange unless you work on it. And remember that we've set these to our unknowns. The reason I picked x for that one and 1 minus x for this one is so I'd only have an equation in one unknown. If I pick y for that one, then I've got 2 unknowns and we're technically screwed. Right? You can't solve an equation, a single equation in 2 unknowns. And so this is the fractional abundance of that one. This is the fractional abundance of this one. And the way we calculated before during lecture was we took the fractional abundance times its mass number, or the atomic mass. And then we took this one times its atomic mass, and we add those together. It's a weighted average. That's all I'm doing here. I'm just substituting an unknown rather than a fractional number. Okay, so it's not that strange, really. All right, so with this equation, we get 63x plus 65 times 1 minus x is equal to 63.55. Okay, that's what that says. Now just solve for the unknown. We expand that parentheses. That's what this is right here. Okay. Then we want to get all our x's on one side and all our numbers on the other side. So this one's going to go over here. This is going to be 63x minus 65x equals 63.55. I'll just go step by step. Minus 65. The plus on this side is minus on that side. There's our equals. So far, so good. Okay. So this is going to be minus 2x, correct? And this is going to be, let's see if I can do it in my head. One 1.45. Yep. Minus 1.45. That was a bigger negative than this positive. And we got negatives on both sides, so the negatives cancel. And then x is equal to 1.45 divided by 2. Which is 0.75. Right. And that's the fractional value. The percentage value would be times 100, wouldn't it? Right? Approximately 73%. There's no 73 up there, but there's none of the above up there. So you pick the one that's closest, which is 70%. Okay. I started off with a bad one, didn't I? That's number 1. All right. Scroll to the next one. 3, I can get 3 and 4 on there. 3. All right. The average mass of a carbon atom is 12.011. 12.011. That's the average atomic mass units for carbon. Assuming you were able to pick up only one carbon unit, which they should say carbon atom, the chances that you would randomly get one with a mass of 12.011 is what? It's a trick question. Just to see if you were paying attention during the lecture. The probability is 0. 12.011 is a weighted average of all the isotopes naturally occurring. Right? So you're never going to find one that's 12.011. You're going to have some that are 12, and you're going to have some that are 13 point something. You're going to have some that are 14 point something. And you average them together, weighted average them together, and you get 12.011. There's no atom in there that's that weight. That's that mass. Right? So it's 0%. 4. Right. What's the mass of 4 atoms of copper in grams? So we're starting with 4 atoms of copper. And let's look at the answer. Yeah, okay, they're grams. Well, we know A is not going to be it. 254.2 grams. Sometimes when these multiple choice questions are developed, the person doing it will throw in answers that result from miscalculations that students typically make. So the answer's there, but if you calculate it wrong, you're going to find your answer there, but it's the wrong answer. That's why some of these are placed there. So we're going from atoms to grams. Now, what's the bridge between mass and numbers? Molar mass. Molar mass. So we need to get this into some moles before we can go to grams. All right, so how do we get rid of atoms and leave us with moles? Has to be Avogadro's number. How many atoms in one mole? That cancels atoms and leaves us with moles. Okay, so now we can convert moles to grams because we know what the molar mass of copper is. Naturally occurring copper, 63.55. Go. There we go. That's grams. That's what we're asked for. So put in 4. This is the easy part. Assuming you set it up right. Divided, and then 63.55 times. So, only 4. Oh, this is a counting number. I never made this point before. 4 atoms. That's a counting number. It has infinite. It's an exact number. It's like 9 pencils in our earlier example. Counting numbers don't have a limit on number of significant figures. So we can put as many as we want in there. And that looks like there are maybe 3 or in that neighborhood. So 3 significant figures gives us 4.22 times 10 to the 22nd minus 22nd. Okay, that's why the answer is E. I don't know why that's evaded me in the past. That's an exact number, right? So we can pick as many significant figures here as we want. Let's see, I heard somebody ding-a-ling. Curry, Amber, Duncan. Am I missing somebody? No, just Morgan. Okay. Let's see. Now we use papers. Which one of these? I think I do have some papers for you. Yeah, I do. No, I do. Yes, I do. I have two. I forgot to hand them out last time we met. All right. So, four. Now we're going to go to, stop it there at 6. You have a sample of zinc and a sample of aluminum. Okay. That's all we know so far. We've got a sample of each. You have an equal number of atoms in each sample. Okay. Equal number of atoms for each one. Which of the following statements concerning the masses of the sample is true? So we want to know something about grams of each. First one, the mass of zinc sample is more than twice as great as the mass of the aluminum sample. We have the same number of atoms, then we can pick how many we want. That's what I would do. We've got the same number of atoms each one. Let's just say we have a mole of each. Right? So what's the molar mass of zinc? 6538. 38 grams. How about aluminum? 2698 grams for that mole. Okay, so this is about 27. The mass of zinc sample is more than twice as great as the mass of aluminum. Is that right? 27 times 2 is 54. Right? So yeah, it's twice as much. And let's see. We don't have any squirrely ones in there, like 2 of the above, none of the above, so forth. So we found the answer. It's more than twice. If it's the same number of atoms, then that's the mass of that number. 1 mole, 1 mole. So zinc would have twice the mass, more than twice the mass of aluminum. Okay. Probably ought to move that one down to maybe C or D. Just give us some work. All right. Let's see. We can get 7 and 8 on the same screen there. A sample of ammonia has a mass of 43.5 grams. 43.5 grams of ammonia. Do I give the formula? Oh, no. You may not know what ammonia is, right? So if you don't, and if a question like this pops up on a test, just ask me what it is. And I'll tell you, it's NH3 is ammonia. How many molecules are in this sample? So in this case, we don't care about individual atoms. We just want the whole unit. And so if we convert that to, we need to bridge the gap again. And the gap is bridged by molar mass. So ammonia is 14.01 for that ammonia. 3.03 for the hydrogens, right? 3 times 1.01. And so we have 4071. 17.01 is that many moles. So we've got to the mole part. They want molecules. How many molecules do we have? Moles. Molecule. Remember, Avogadro's number is just so many those things. Right? It's how many things are in a mole. That should give us our answer. Dimensional analysis again. I get, let's see, we are restricted here to 3 significant figures. 1.54. Times 10 to the 24th molecules. Now, if the question had been like, how many nitrogen atoms are in that sample? It's 1 to 1, so it'd be exactly the same. One nitrogen for every ammonia, right? Be the same number. If it asks us for how many hydrogen atoms are in that sample, it'd be 3 times that. For every one of these, you get 3 hydrogens. So 3 times that would be the number of hydrogen atoms in that sample. Okay. Okay, number 8. How many moles of hydrogen sulfide are contained in 49.7 grams of this gas? 49.7 grams of hydrogen sulfide. Can you write that compound? Think of it this way. What are the charges on everything in the calculants? -2, yeah. And hydrogen is +1. So it takes 2 pluses and that to neutralize that 2 minus. All right. That's kind of, well, I don't want to muddy the waters too much, but I don't think this is an ionic compound. So we're using one set of rules to solve another problem. But that is the correct name. Hydrogen sulfide is that. Okay. The question was, how many moles of hydrogen sulfide? How many moles of that unit are there? Right. So this is really a one-step simple moles, grams, and a quotient relationship, always molar mass. So we have 2.02, right, for 2 hydrogens. The sulfur is 3207. Add those together. That's 9,043. 49.7 divided by, let's see. I bet we can ballpark this one. Go into this one time with how much left over? Maybe 15 and a half, roughly 1.5. So B would be our best choice out of that one, without even using your calculator. I mean, you can use your calculator. I'm not saying you can't, but in the interest of time, this is a multiple choice. And the answers are far enough apart. So if I get close, I can pick the right answer. That was 8. 10 and 11. Let's see. I got till 2. Actually, I've got only 30 minutes, right? But 1:45. Okay, we might have to bleed over into Thursday to finish this up. 10. For which compound does 0.256 mole weigh 12.8 grams? 0.256 mole. 0.256 mole weighs 12.8 grams. Grams per mole. Molar mass. 0.256, which is 50 grams per mole. All right, let's see which one of those comes close. Let's see. A is C2H4O. C2H4O. Well, this is 2 times 12.01, which is about 24. This is about 4. This is 16. All right, so I'm just going to estimate. See if I can get close. 24 and 16 is 40, 44. Approximately 44. That's not it. Carbon dioxide. Okay. 2 times 16 is 32, right? And 12, right, approximately. So that's 44 again. Approximately. Everybody see what I'm doing here? I'm saving time on the test. CH3Cl. CH3Cl. Methyl chloride. Okay, so this is 12, 3, and this is about 35 and a half. So 12, 15. And yeah, that was it. Methyl chloride. And we can throw which compound is okay, great. All right. Yeah. D is C2H6. Right, that'd be 24 here and 6 there. Right, that's only 30. All right, so your best answer is C. Actually, if we took this out to the first decimal point, you could probably argue that it's not close enough and say none of these. Right? If I marked it wrong, you'd have to come argue your point though. Show me your work. But you could probably make a case for getting the points. 11. Calculate the molar mass of barium sulfite. Now you got to be able to write the compound. Barium. Now that symbol. Sulfite. There's no compound up here that, no element up here that will give you sulfite in the name. Sulfide, yes. If it's just sulfur, it's sulfide. Sulfite, that's a polyatomic ion. So you may have to look it up. It's SO3 with a 2- charge. How about barium? Barium's an alkaline earth. So it has a 2+. Right? So that's it. Just need one of these, one of that. So now we look up barium, which is 137.33 grams per mole. We have one sulfur, which is 3207, and 3 oxygens. Was 3 times 16. Click, 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 click. 48. Right? 2 of them is 32. Add 16 to that, you get 48. Okay, so this is carry the 1, 4. And let's see, 17, carry the 1, 5, 8, 11. 217.40. Is that one up there? Yeah, E. Grams per mole for that formula unit. Right, let's do some scrolling here. 13, let's just get 13. Oh, I did put it in this one. I added ammonia in there. I don't think I did it on your sheet though, did I? I did. Oh, good, good, good. 13. What's the mass of 6.761 mole sample of sodium hydroxide? 6.761 mole sodium hydroxide. We know sodium's in there. Hydroxide is, it's polyatomic. The end. Other way around. OH. OH with a -1 charge. -1 plus 1, that's it. Okay, now we can answer the question. What's the mass? So we just need to cancel the moles and leave us with grams. So the molar mass of sodium hydroxide, sodium is 2431. Oxygen 16, hydrogen 1.01. 7, 11, 3, 4, 41.31. Go. So you just multiply those two together. And you should get 270. See, is that reasonable? What's 7 times 4? 280. Yeah, it's close enough. I'll just rounding it off in my head to do an estimate. Just to see if I was in the ballpark. Sure enough. Okay. 4 significant figures. All right. 13, I think 15 is on the menu. There we go. 1 molecule of a compound weighs 2.93 times 10 to the minus 22nd grams. This is 2.93 times 10 to the minus 22nd grams per molecule. Okay, we're given that. The molar mass of this compound. We got that many grams per molecule. What's our conversion? We want to convert molecules to moles. How many molecules are in a mole? Right. I'll multiply that one times that one. And you get, I better do that. It's swimming already. 6.022, 8.23. 3 significant figures. 176 grams per mole. With molecules canceled. Leaves us with grams per mole. That's D. Okay. Have I caught any that catch your eye yet? Maybe not. 17. Okay. The compound is composed of element X and hydrogen. So it's got X, hydrogen. I don't know where the hydrogen goes. It's hydrogen here. Doesn't matter. Analysis shows the compound to be 80% X by mass. So it's 80% X. Okay. Mass. Right. So what does that make hydrogen? 20% hydrogen. Okay. With 3 times as many hydrogen atoms as X atoms. So we got 3 times as many hydrogens as we do X. 3 of these for every one of those, right? Okay, so far we're extracting information from the problem. Which element is element X? All right. So how do we know, how can we find out X? We can't get at the number of protons, can we? I don't see any way to the protons. Maybe we can get to the molar mass. How about that? What if we have 1 mole of that compound? We have 1 mole of the compound, we have 1 mole of X. And let's see, if we have 100 grams of each one, right? Assume 100 grams. Then we have 80 grams of X and 20 grams of hydrogen. I'm not sure if I'm following the sheet or not. I'm just working it out. All right. So if we got 20 grams of hydrogen, then how many moles of hydrogen do we have? Let's 0.01 divided into 20. That's 19.8. 19.8 grams of hydrogen. So if we had, oh, I'm sorry, grams, moles. That many moles of hydrogen. Okay. If we have this many moles of hydrogen, how many moles of X do we have? The ratio is 3 to 1, isn't it? Right. This many moles of hydrogen we have 3 moles of this for every 1 mole of that. Then we can divide 3 into 19.8 and find out how many moles of X we have. 6.6. So we actually have 6.6 moles of X. We have moles of X, we have the mass of X. We can calculate its molar mass, can't we? Did I lose anybody yet? Okay, so we have 80 grams per 6.6 moles. That's about 12.1 grams per mole. So what's the closest one we can come to if we look on our periodic table? Looks like it's carbon. Within experimental error. Everybody see how I got that? I probably should have started with, well, I did sort of start with, how do we identify an element when we don't know the number of protons? The only way you get it at is molar mass. So that's where I was headed. Yeah. Okay.
So, because we found out that there's 3 atoms of hydrogen, so then you must know that the X has a -3 charge. So if you look at what all of the atoms have a -3 charge.
Oh, on your periodic table.
Yeah. Well, no. They're taking a look at the check this out, like, oh, this is the other.
Didn't work.
No, my brain totally like filled in a blank.
Okay. Well, that's one way to fix it. Is that the way I did it in this thing? 17. Yeah, that's the way I did work the problem there. I thought it sounded familiar. But if you're asked to identify an element, you don't know the number of protons, you're only left with molar mass. You got to find a way to get the molar mass. Okay, 17. We have 15 minutes. Let's see how many we can get in that time. Let's see, 18. Which compound contains the highest percent of mass by mass of hydrogen? Okay, in this one, we need Henry Ford. E, HF, H2S, H2S4, H2O, and HCl. Percent by mass. So percent by mass is going to be and this is hydrogen. So this would be the molar mass of hydrogen, divided by the molar mass of the compound times 100 for every one of them. In this case, hydrogen, we only got one hydrogen, 1.01. And what's the molar mass of HCl? 1.01 plus 3545. Six, 4, 6, 3. 36.46 times 100. Okay. 136.6. So that's 2.8%. Right. Okay. But this one, 2 waters, 2 times 1.01. What's the molar mass? Well, it's that plus oxygen times 100. Okay. I get, let's see, 100 times that. I get 11.2%. Okay. And we just do it the same way each time. So 2 hydrogens here, 2.02, 2 hydrogens here, 2.02, 1 hydrogen, 1.01. And we need the molar mass of each compound. So 2.02 plus sulfur, 3207. And 4 oxygens. 4 times 16 is 64. 16 times 16 is 32, and 2 times that is 64. Right? 4 times the number is the same as 2 times 2 times 64. 98.09. Times 100. And 2.1%. Okay, how about this one? 2 of those, and 2.02 plus sulfur, 3207. 2.07. That is 5.9. Oh, I forgot to write the value down. And then this one has 1.01 plus fluorine is 19. Yeah, 19. Okay. So that's 18, 19, 20.01. Let's start that over. So it's 5.0. Okay. So the one with the highest percent hydrogen is that. All right. 18, 19. Some of these problems, the only way to work them is just bulldogging. Substance contains 35 grams of nitrogen, 5.05 grams of hydrogen, 60 grams of oxygen. How many grams of hydrogen are there in 153 gram sample? Okay. So it's a takeoff on 18. We want to know grams of hydrogen. Okay, so we need a percent hydrogen. Actually, the fraction of hydrogen would be better rather than percent. So what we want is 5.05 grams of hydrogen. 5.05 grams of hydrogen. And then the total is 5.05 plus 35 plus 60. This would be the fractional composition of hydrogen. This is 100.05. Divide that into 5.5. That's 0.05. Yeah, 047 fraction. This is grams of hydrogen per gram of sample, because we didn't multiply by 100. So now we've got this conversion factor, and we've got 153 gram sample. And so that will cancel that and leave us with grams of hydrogen. 7 points. Pretty significant figures. 7.72. Okay. $19. See, let's roll 22. Each molecule of testosterone contains 19 atoms of carbon. Plus other atoms. Hey. The mass percent of carbon in testosterone is 79.12%. 79.12% carbon mass. Okay, what's the molar mass of testosterone? All right. 19 atoms of carbon. All right. If it has 19 atoms of carbon and there's 1 mole of it, right? There's 1 mole of this carbon and it has 19 atoms. Then 19 times 12.01 times 12.01 will give us grams per mole in that compound. Actually, grams in that compound. Yeah, just grams, because this is grams per mole. And this is, if we have 1 mole of compound, then there are 19 moles of carbon. Everybody see that so far? Okay. So if we assume 1 mole of testosterone, then we have 19 times 12.01 moles of carbon. Let's see, 19 enter 12.01 is 228.19 grams of carbon in 1 mole of testosterone. Right? So now, why am I? Oh, hold on a second. See, they anticipated my mistake. C is not the answer. All right. Maybe we'll approach it differently. Say instead of 1 mole of testosterone, we have 100 grams of testosterone. How about that? If we have 100 grams of testosterone, then 79.12 grams is carbon. So how many moles is that? 12.01 grams. That would be 6.588 moles of carbon in a 100-gram sample of testosterone per 100-gram sample. Okay. What we want is molar mass of the compound. It's this many moles of carbon per gram of the compound per gram of testosterone. 100 grams of testosterone. How do I get from that to molar mass. I want grams of testosterone per mole of testosterone. So we can write it this way, right? That's an equivalence per 6.588 moles of carbon. Correct? Okay. So now what I want to do is end up with moles per mole of testosterone. So how many moles of carbon are in a mole of testosterone? 19. Okay. So far, getting rid of this one, and leave us with grams of testosterone per mole of testosterone, which is what they're asking for. $288. So that's why E is the answer. I'm not sure why this didn't work. Yeah. We only got 3 minutes. Let me look at the next one and see if it can be done quickly. If not, we'll stop here. Yeah, we can do 24 pretty quick. An oxide of iron has a formula Fe3O4. What's the mass percent of iron? Okay, so we want what's 3 times iron? 55, 85. Okay. Then 3 times 55, 85 plus 4 times 16. 100. And that should give us 72%. Now, if you try to balance the charges here, this is -2. That would be -8. Right? 3 doesn't go into 8 an even number of times, does it? To find out what the charge on iron is. So what this is a combination of 2 compounds. This is the simplest formula that we can get for it, but I think it's a combination of FeNO and Fe2O3. All right, that's 24, and that's going to be where we stop. Let's see. How do I think what I'll do is highlight the whole thing. That'll show me where we stopped. And now we get to do some fun. Wait a minute, we're missing some people.